Welcome everybody, it's Ramachandra from CIVIL-MECH-MATHS concepts. Today I am dealing with very important concept of fluid mechanics, which is the pump design and also pump system design, and I will clear the concepts about the pumping design and pump system design so that you will be able to design any pump for fluid mechanics and fluid mechanics systems with ease, and you will understand the concepts very easily, and numericals will be done in the next class. I have taken an example. Best of luck. Please listen to my lecture. Good morning everybody. It's Ramachandra from CIVIL-MECH-MATHS concepts. Again, as I promised, I am continuing with the numericals in fluid mechanics. This is the 11th lecture on fluid mechanics. Kindly see my all 10 lectures previously I have released, and I have spoken about the first 1, 2, 3 chapters where prelims are discussed, like definitions, pressure calculations, velocity calculations, and different types of forces I have discussed. Now I am doing for the last 2 classes I have been doing this numericals. In the last 2 classes I have done 2 numericals which were very interesting and very interactive. It's not that numerical should be values are given to you and you will be solving the problems. Instead, you understand the problem well and you create your own problem and solve it. Now in the last 2 classes are also the problems were typical and values, full values which are required are not given, and we have derived our own formula. And from that we have done our calculations. Similarly, in this also, what we will do? We will formulate the problem. As a design engineer, you have to calculate the power required for pump to draw water from the underground tank to a tank where it is at a higher elevation, and in between 2 intermittent tanks are there. That means from A you will be going to A dash, or we can say C, and from there we will be going to D. Here let us say it is C, and next one is D. Now let us see what happens. Now, what are the things we require to solve this problem? Question is in front of you, geometry is in front of you, and the dimensions are in front of you. You have to find out the power required for the pump to pump water from point A to point B. Point A is underground, it's an underground reservoir, and point B is above ground. In between, 2 intermittent storage facilities are also there. Now, what we have to do is to formulate the problem. We have to find out what are the parameters required for us to solve this problem. If you go in this way, you will be able to easily formulate your own problem and you will be able to solve. If I give the parameters also, you will find a formula and you will just substitute it. That's not the way how we should go for the numericals, especially in engineering problems. Now in this, we have told it is A, and this one is, next one is B, and next one is C, and last one is B. And first one, from ground level to pump level, there is an elevation of, what is the elevation? There is an elevation of 30 meters. from pump to other reservoir, not up to the other reservoir, in between the other reservoir, let us say this is the pump, this one is the pump, let me write it as pump, and this is the reservoir C, this is another reservoir D. Reservoir means don't think that there will be a big reservoir like in your city municipality reservoirs will be there outskirts of the city. No. Reservoir is a place where water is stored or a fluid is stored. A reservoir can be of any size. It's only a what you call name given for storing container of a fluid. Heat reservoir, like this water reservoir, fluid reservoir, it's a reservoir. A is below ground, groundwater is there, and to a height of 30 meters, one pump is fixed, and after that, for 500 meters, the pipe is gone half a kilometer. Again there was an elevation to the pipe about 20 meters, and it is connected to a reservoir after 50 meters connection, and from that reservoir again 50 meters pipeline has gone parallelly, and again it has come down by 35 meters, the water is flown into another reservoir D, and from there the final reservoir B, which is at a height of 120 meters from D, the water is gone. Water flowed. Now, this distance also we require. This distance, let us say 100 meters. Nothing is to scale. It is only for your understanding I am doing it. Let us say this distance is 50. Now, I have given the distances. I have given the heights. When length and height is given, can we find out the power required for the pump from a particular height to the particular height pumping? I have given diameter of the pipe is same everywhere, a general statement I made. Now you tell me, what are the things required for designing this pump? Just think over now. Here, let us see. What happens when pump sucks from the underground level? That means there is a amount of energy consumed. That means some energy is required. Some energy is spent in sucking the water from underground 30 meter to a 30 meters height. That means there is an expense. There is a energy expense is there. Now, when water has come to pump, in pump water is there. Now water is to be horizontally flown. Does it flow automatically horizontally when there is no slope? Water flows from a higher slope to lower slope. That is natural. And when it goes from a lower slope to higher slope, then that will be forced or using a pump. For horizontal flow also pump is required? Yes. For horizontal flow also pump is required. Here also energy is expended. Again from here to here energy is expended. Here to here energy is expended. From here to here energy is expended. From here to here what happens? It will fall by gravity. Please think over. What happens? Is energy is expended or it falls by gravity? Please think over. Next, from here to here, energy is expended. Here to here, energy is expended. Now, let us try to understand the concept of it. Whenever I spend some energy, what happens? That energy I get from some electrical power or a mechanical power. I lift some item from ground to the top. Either I use some mechanical instruments to lift it, mechanical power, or I require an electrical power. Now let us say, here everywhere electrical power is used. Electrical power. First assumption what we are making is electrical power is used. Here you see, I will not tell anything. From the diagram itself, we observe the things, we understand the things. That means, first of all, pump requires an electrical power. How electrical power is measured? Electrical power is measured in electrical power. Either it can be watts or it can be HP. You might have heard. Put some 1 HP motor, 2 HP motor, 3 HP motor, you have constructed a house. You wanted to put some motor to lift the water from underground to your upstairs. Somebody say, Mistri will tell, 1 HP motor will be sufficient, 2 HP motor will be sufficient, 3 HP motor will be sufficient. Very few people talk in watts. What is the relation between watt and HP? You have to understand this. It is required. Because in the examinations usually people get confused here only. Watt and HP. What is watt? What is HP? HP is the horsepower. What is the SI unit of the power? Watt is the SI unit of the power and HP is general way of expressing the power. While going for purchasing a motor, we say, please give me 2 HP motor, please give me 3 HP motor. We don't say, give me this number of watts. For convenience, HP is being used. 1 HP, please remember this. 1 HP is equal to 746 watts. We can say approximately, I am telling you. We can even say 736, 746. 1 HP is equal to 746 volts. This watt is energy in joules per second. Please remember this. Energy is measured in joules. Energy joules is nothing but Newton meter per second. Joule is nothing but Newton meter. Newton is nothing but kg meter per second square into meter per second. You please try to understand these concepts very clearly. What is Newton? Newton is equal to mass into acceleration. Mass into acceleration is kg into meter per second square. Newton meter per second square is meter per second square. That is equal to mass into acceleration into v. Can we say that? Can we say this? Just please try to understand this concept. I am not worried about the quantities. Please try to understand the concept. The units of power, watts, is nothing but units of multiplication of mass into acceleration into velocity. Can I write it as acceleration whenever we use the gravity? mgv. Let us say, what is there? Nothing wrong. G also has the same units. I am here only comparing units, comparing dimensions. Sometimes engineering can be done very easily by comparing the dimensions. What is mass? Mass is equal to kg. Kg is equal to density into, let us write it in terms of density, volume. Do you agree? Because density is kg per cubic meter into cubic meter. That is equal to kg. Please see how beautifully we are deriving our required equations. We are not going into the complexities of the equations. Simple method. Then can we put this way? Rho into V. Here V is volume. Can we say like this? Instead of volume per second. Can we say like that? Rho into volume by second. Can we say this? That means mass is equal to rho into second. Rho into Q into second. Do you agree? Where Q is flow rate. This is very important. Either this can be cubic meter per second or liters per second. This is the flow rate. This is volume flow rate. It's not mass flow rate. Mass flow rate is different. That is kg per second. It is volume flow rate. Flow rate cubic meters per second. This Q is there. Then M is equal to rho Q into Are you able to understand till now, till this time? No. What is power? power is equal to mgv. Here it is velocity. From this equation, this is equal to mgv is equal to, what is m? M is equal to rho q into second into g into v. What are the dimensions of v? Meters per second. Rho q into g into meters per second into second. Then second will go up. Rho q g into h. Meter is nothing but height. That means power is equal to, power of the pump is equal to rho q g h. This is one of the most important formula that is required to be understood well, that is required to be by-hearted by mechanical and civil engineers for designing a pumping system. Now, we have got the formula power is equal to rho q gh. Please remember this formula. It's throughout your lifetime it will be useful. Not only for the examination point of view, for engineering calculations, during your professional life also, throughout your lifetime, this particular equation will be very important and useful to you. Then what are the units? Rho q gh, rho g qh you can call anyway. Now, what are the units? Rho is kg per cubic meter, g is meter per second square, q is cubic meter per second, h is meter. This is nothing but kg meter per second square into meter whole per second, that is equal to ma we can even say this is kg, meter per second square is Newton, Newton meter per second, that is equal to joules per second. Joules per second is equal to watt. That means by applying the formula in SI units, we can find out from rho q gh, power in watts. Please remember this. And once watts are known, 746 watts is equal to 1 HP. That means almost 3/4 of approximately half kilowatt is equal to 1 HP. Please remember this. If somebody gives the power in kilowatts, 75% of it is HP. Now, what we are required to find out here is power required for the pump, to pump from certain height to certain height. Now here what are the parameters to be known? Q is required, H is required for finding power P. P is equal to power P is equal to rho Q GH. Why I am repeating one or two times? Because it's a very, very important formula. People make lot of mistakes in units and they will end up with some other answer. Please don't do that. In simple examinations, a simple question may be given. Some distance may be given in centimeters or kilometers, and you are asked to find out the power in watts. You will just go and blindly multiply. Please see the units also. SI units, SI units. Please apply SI units. Now, from the given problem, now you tell me. Just let us start thinking. Power means energy. Energy is not only expended in the height, it is spent in moving the product or fluid in the horizontal line also. In that case, is this formula P is equal to rho QGH valid or not? Under what conditions it is valid? Under what conditions it is not valid? If it is universally valid, then what are the assumptions you have to make and what are the changes you have to make in the formula? That is also very much interest to engineers. For example, if I consider height, what is the net height? Here it is 120 meters, here it is 35 meters, here it is 20 meters, here it is 30 meters. Which height to be taken? Think over it. Which height to be taken? Is it the net height to be taken from one point to another point? Is height a vector quantity or a scalar quantity? Does height has a direction for measurement or it does not have any direction for measurement? What to do? Think over. Now, I want to introduce a concept where in horizontal movement of the product or fluid in a pipeline also requires power consumption or energy expenses. That is because the movement of the fluid in a pipeline from one place to another, when the elevation difference is 0, even though elevation difference is 0, that rho Q GH is equal to 0, there will be a power consumption for moving that liquid from one place to another place. That is due to the fact that there is a mass transfer, there is a product transfer, there is a fluid transfer, and this transfer can be obstructed by the friction within the pipeline. That is what is called as friction losses, HF. HF is equal to FL V square by 2GD. This formula is also a very famous formula in pipeline transfers. HF is equal to FL V square by 2GD, where F is equal to friction factor. Very important concept as far as the fluid flow is concerned. L is equal to length of the pipe D is equal to diameter of the pipe. V is equal to velocity of the pipe, velocity of the fluid in the pipe. If I say, for simplicity, as an introductory course on fluid mechanics, if I say my friction factor is 0, then HF will be 0. Frictional resistances are neglected. If frictional in the question, if it is given that frictional losses are neglected, then we can assume this. Otherwise, we should not assume this. For simplifying this model, you can treat this as a model. Then, length will not become a constraint while calculating the power required from the pump if friction losses are neglected. Then, there is a straight line and there is a line like this. Which line requires more power? Just think over. In the problem I have given, there are about 90-degree bends. 1, 2, 3, 4, 5, 6 bends are there. This is equal to 90-degree bend. There are 6 bends. At 90-degree bend, what happens? Product comes this way. Fluid comes this way. It hits the blind there. Then it takes a turn in this way. Here at this juncture, junction, loses its momentum. From conservation of momentum principle, when the direction changes, it loses its momentum, and that whatever loss is there, that is converted to the loss of energy. That means at bends, there can be a heat energy which is lost to the atmosphere. Friction also causes heat energy which is lost to the atmosphere. Frictional energy is also lost. A loss at the bend is also a loss. Hence, there will be a loss in the bends, especially 90-degree bends. When there is a loss, in the momentum and additional expense of energy to overcome this, to maintain the flow rate, then these losses are called as losses due to geometry of the pipeline. Bends, 90-degree bend, 45-degree bend, 30-degree bend. Bends can be of any shape. If these bends are considered, if losses at the bends are considered, then the power required will be more. That means total power required is equal to general from the formula as usual plus power for overcoming the friction plus power for overcoming the geometry. If geometry and friction play a role, finding the power requirement from rho Q GH will not be workable. That will not be workable. Hence, until and unless the geometrical losses or losses at the bends or any other losses due to any geometry are neglected, you cannot neglect this loss. Friction can only be neglected when it is given in the question that friction losses are neglected. Then next comes, we just see how we are analyzing, under what conditions rho Q GH is applicable. At point C, this is C, from here up to 35 meters distance from C to D, it is like a waterfall in the pipeline. Water is moving, there is a bend also here. Water is moving in a closed conduit. But there is a gravitational pull also. In addition to your regular velocity flow. When product is pumped from the pump here, it goes with a certain velocity V and goes to the top. It goes into the tank. If the initial reservoir levels are at par or at level with the level of the pipe at which this is connected, then there will not be any loss. Fluid will be moving like this from here. Otherwise, fluid will be settling in the tank, and once the product in the settled tank overflows, then only fluid moves out. That means there is a loss of velocity. There is a loss of velocity in this portion also. Wherever there is an obstruction, wherever there is a loss of velocity, loss of velocity is nothing but kinetic energy is half mv square. Kinetic energy is lost. Once kinetic energy is lost, there is a loss of kinetic energy. That means velocity is lost. Once velocity is lost means the fluid flow rate is lost. That fluid gains the potential energy and kinetic energy is lost, and fluid gains the potential energy, kinetic energy is lost. Hence, the Q is lost. What is the formula for Q? You please remember this also, very important formula. Q is equal to cubic meter per second is equal to meter square into meter per second. What is meter square? Meter square is nothing but area of cross section into meter per second is velocity. Q is equal to AV. This is called as the continuity equation, conservation of mass. Conservation of mass. continuity equation. This is conservation of mass. Q is equal to AB. A is area of cross section. V is velocity of flow of liquid. Now you just see how many formulae we have derived. Power is equal to rho Q GH. What is Q? Q is equal to AV. Rho AV GH. Please try to remember this equation. Power is equal to rho AV GH. This is also one of the most important equations. One is rho QGH, another is rho AVGH. This AV is nothing but Q, rho AVGH. This is how the above question has to be analyzed step by step, has to be solved, and there are many unknowns here. Bend loss constants I have not given. Diameter of the pipe I have not given. The flow rate I have not given in cubic meter per second. And rho, you know, 1000 kg per cubic meter, that is density. Rho you know, G you know, that is 9.81 meter per second square. H's are known. Now, is the velocity in the pipeline will be same as the velocity, is the velocity in the pipeline till the reservoir entrance will be same as the velocity in the pipeline after the reservoir exit? Is it here the velocity V will be same as this velocity V? No. Those factors I have not given. The two reservoirs I have not given. The reservoir geometries I have not given. That means a pump design is a function of, just please understand this, pump design, the power is a function of, power required for a pump to pump something is a function of rho of the fluid, area of cross section, velocity of the fluid in the pipeline, then G, then height of flow and geometry of setup. A reservoir can be a closed container, or a reservoir can be an open to sky. This reservoir can be, I told you, reservoir does not have anything what you call, that reservoir means it should be open like in a river. No. It can be anything. It can be either closed. I can keep it as a closed. And I have written, put it as a rectangle. It can be a trapezium, closed trapezium. It can be a closed oval. Why not? That's a reservoir where I am reserving. I'm keeping some fluid inside it. Yes, that's the reservoir. Now, this is what is the science behind the pump design. Why I have taken this as a topic of discussion today? I didn't solve any numericals here. The reason being, I want you to be familiar with the systems first, so that we will do the numericals. In the next class, we will definitely start with some good numerical on this pump design. You just see, first assumptions we made, we created our own formula. Usually, electrical power in SI units is in watts, whereas in commercial sense, it is in HP. And watts is nothing but energy per second, that is joules per second. Joules is nothing but force into distance, that is Newton meter. The Newton meter per second is equal to watts. That's nothing but, as per Newton's law, mass into acceleration, kg meter per second square into meter per second. That is joules per second, that is watts. Power is equal to MAV, from where we got MGV. From then we have got rho V is equal to rho into volume per second, that is Q, rho Q into S. M is equal to rho Q into S. Where Q is the flow rate, capital Q, it's not small q. Capital Q, flow rate, cubic meter per second or liters per second. Power is equal to MGV, that is rho QS. GV, that is equal to rho QGH. We have derived rho QGH, and from there we have got the units, and we got that 3/4 of the kilowatt is equal to 1 HP. 746 watts is equal to 1 HP. Please remember this. And power is equal to rho QGH in SI units, when rho is in kg per cubic meter, Q is in cubic meter per second, and G is in meter per second square, and H is in meters. And is that rho QGH is valid under all the circumstances in a pump design? No. H is affected. The effective H is affected by the frictional loss in the pipeline. HF is equal to FLV square by 2ZD. That's a very famous equation, where F is the friction factor, L is the length of the pipe, D is the diameter, E is the velocity of the fluid in the pipe. If frictional losses are neglected, then we can say HF is equal to 0. Is it frictional losses are only there in the pipeline motion? No. There are bend losses, there are valve losses, sudden closure losses, sudden opening losses. There are different types of losses in the pipeline. Those losses, if you feel they are negligible, then only we can make other losses as 0. There will be, in total, the power required will be from the rho QGH plus frictional losses plus geometry losses plus, we can say, other bend and valve losses, other losses. Power required for other losses. From there, we got the formula. Q is equal to AV, area into velocity. Area is the cross-sectional area of the pipeline. P is equal to rho QGH is equal to P is equal to rho AVGH. That means power required is the function of density of the fluid, cross-sectional area of the pipeline, velocity of the flow. G, why G I have written, even though it's a constant on earth, if the motion of the pipe product is taken at a higher altitude, the G value reduces or increases according to the altitude. Then height, the height is effective height. Then geometry of the setup. The reservoirs, pipelines may not be fully circular. There can be geometrical problems due to the roughness of the pipeline, due to the bends in the pipeline, due to the restrictions in the geometrical constructions at the site. That is geometry of the setup of the system. So ultimately we have come to a conclusion that Designing of a pump is not a that easy task. It involves all these tasks, understanding of these tasks, and wherever possible in the questions, if they are given as neglected, make them 0 and apply the formula P is equal to rho Q GH and get the values. Best of luck to everybody. In the next class, we will do a numerical. This numerical in this class is only concept understanding numerical. And you can try the question only up to half. For example, from A to C, you can try. From C to B, we can try separately. We will break the system up to C. C to B we will try separately, and A to C we will see separately. What is the difference between C to B and what is the difference between A to C? That we will see definitely. And whether C to B is possible or not. And if A to C is possible, what will be the pumping capacity required? What is the power required for the pump to water from A to B? I have asked, but we are cutting it into different parts and analyzing it individually. This is what is the conceptual understanding required for solving this type of problems. Thank you. Thank you for listening to me. It's Ramachandra from CIVIL-MECH-MATHS Concepts channel. If the way I am explaining the concepts, if you feel comfortable, please subscribe to my channel. CIVIL-MECH-MATHS Concepts. I am mainly interested in developing the concepts for all of you, so that if concepts are there with you, applying the formula is not a very big task for an engineer. CIVIL-MECH-MATHS Concepts. It's Ramachandra again. Best of luck to everybody. In the next class, maybe in a couple of days, I will come up with at least 2 small numericals. This is a bigger one to make you to understand the importance. Once you understood the importance and the concepts behind in pump design, in the next class you can see small problems in competitive examinations. You will be easily able to solve them without any issues. Best of luck to everybody. If you understand these concepts clearly, you will definitely excel well in the examinations and in your life also while dealing with the engineering problems. Once again, thanks a lot for listening to me. Best of luck to everybody. It's Ramachandra from CIVIL-MECH-MATHS Concepts.